We have already implied that the El Nino and La Nina are coupled ocean atmosphere phenomenon, so we must look at the annual cycle of the upper Pacific Ocean as well. There are some very interesting features which some of you may be already aware. We are looking here at the mean annual cycle averaged between 5 north, 5 south in the Pacific Ocean. So that's kind of the main dominant meridional scale of the processes involved in the El Nino, other than the perturbation to the Hadley cell and the Walker cell and so on. So we're looking at SSTs, depth of the 20-degree isotherm, which is considered the thermocline in the deep tropics. In the higher latitudes it's not that well defined, and the mean sea level pressure in hectopascals. Okay, so if you look at sea surface temperatures, imagine now you are averaging over the deep tropics, -5 to 5 south to 5 north, and the warm pool remains essentially warm in this deep tropics throughout the year, with a little bit of movement of the sun making a difference here. And you can see as you go eastward, in the east, for example, get over here, and there is a strong seasonal cycle here. You have cold SSTs in the beginning, so maybe we should go, this is showing December, so maybe we should go down January, February, March, June, July to December. So if you start here, you're starting the year slightly colder in the east, and then comes spring season when the sun is crossing the equator into the northern hemisphere, and the entire tropical Pacific relaxes. So the trade winds relax, sea surface temperature gradient relaxes, as you can see here, and yet El Nino doesn't happen every year. Okay, there is no positive feedback kicking up during every season, but every year does have this relaxing of the cross equatorial or east to west SST gradient, and then the trade winds begin to get stronger as sun crosses into the northern hemisphere and the ITCZ follows, and the southeast trades cross equatorial winds get stronger, Ekman divergence and upwelling get stronger. So August, September, October you get very strong upwelling, and you get very cold SSTs, and the sea surface temperature gradient is maximum. And then again you get sun coming back towards the south and going back towards the relaxation of the upwelling and so on. Corresponding to that, you can see that the thermocline itself does have a seasonal cycle which is somewhat out of phase with this, because it's a bit complicated, but nonetheless I'll explain in words and then you can look up. So Ekman divergence in the east is pushing water away from the equator, and cold waters are coming up, so that's going to pull up the thermocline or the 20-degree C isotherm. So in a mean, it's obviously much shallower than in the west, which we already saw and we will see again. But at a seasonal time scale, as the winds get stronger, we said this upwelling is caused by strong cross-equatorial winds. Those winds also have strong turbulent kinetic energy. So as divergence gets strong and upwelling gets strong, the winds are also mixing the water and entraining waters from below into the surface, so the mixed layer gets deeper, and thus the thermocline is, you can see, slightly offset from the coldest temperature. It's somewhat shallowest over here in June, July, August, but this one is much more in August, September, October. So those are subtle differences, but year to year it changes a lot, so you don't have to worry too much. But you do need to remember that there is a spring relaxation here as well, and there is this strong east-west gradient, and the thermocline annual cycle becomes fairly weak as we get towards the dateline and so on. Corresponding to that, obviously there is a mean sea level pressure. You can see that the coldest SSTs are associated with a high sea level pressure. In the west you have a stronger seasonal cycle in the sea surface sea level pressure. In the west, in the east, it remains fairly high throughout the year, and only during La Nina it gets less. during spring warming it gets less as well. So this is the annual cycle, and if you look at the annual cycle of the upper Pacific Ocean in terms of temperature profiles with depth going from west to east, now you clearly see the thermocline slope. So here is a strong thick line of 28 degrees, 24 degrees and 20 degrees. So this is the strong thermocline, which is the word thermocline itself is temperature gradient. So that's the strong gradient you are seeing. And this is the warm pool. You can almost see the volume of warm water that's sitting there. This is the annual mean, and this is for January, April, July and October. So you can see the seasonal cycle in the east, which is somewhat stronger than here, but this strong front around the dateline is also there in salinity, because there is much more rain here than here, and there is also fronts in carbon dioxide fluxes and so on and so forth, which we won't get into. But you can see that the annual cycle in the upper ocean is fairly clear, but it remains over the seasonal thermocline, basically above about 200 meters, and then below that there is not much perturbation on the annual time scale. So this turns out to be important, that the upwelling warm water accumulation in the west and the slushing during the El Nino and La Nina are all essentially upper ocean processes. Mean annual cycle of the wind fields, this is the surface zonal wind and meridional wind. You can see that the trade winds wax and wane as the ITCZ moves back and forth. Here you get the monsoonal forcing, so you get westerlies coming in on the far west from the maritime continent, Australia, New Guinea region, whereas the meridional winds get very strong during the summer season, when the ITCZ is far to the north and the convergence is strong across the equator into the ITCZ, and they relax also during the boreal spring season, when the entire east-west gradient weakens. This east-west gradient, because we are at a low latitude on the equator, 5 south, 5 north, Coriolis is weak, so the east-west SST gradient itself creates strong pressure gradient, which can drive strong zonal winds, which become critical for El Nino and La Nina as well. Okay, so then we'll come back and look at the interannual variability of the annual cycle. These seasonal variabilities of the atmosphere, the ocean, and their interactions should be very clear in your mind. They should be like, you should know them like the back of your hand. They are very simple. There is complicated heat exchanges and advection and entrainment of heat involved in determining the SSTs at seasonal and interannual timescales, but nonetheless you should be able to explain them very clearly just from looking at these figures and have these in your mind clear as day. Okay.